Okay. Hi, everybody. This is going to be a small introduction to computer vision. It is not going to be very high level. No, I mean, it's not going to be very difficult. It's going to be very um, um, uh, really a small introduction. So I hope that you enjoy it. Let's start. So, okay, first, there are some things that we need to know about the difference between computer vision and machine vision, maybe image processing, and how these concepts are inside artificial intelligence. Sometimes they are not very commonly uh, seen as part of artificial intelligence, but in some cases they fall into that definition because of the techniques that they are using to develop some things. So in between machine vision and computer vision, we can say that one of the different some of the differences between them are that machine vision is more focused to all the objects that we need, to all the devices that we need to capture the images and maybe make a pre-processing of the images before get the algorithms that computer vision is taking charge of them. By example, if we want that when a self-driving car knows about the environment, then all the devices that the self-driving car has in the technical in the hardware, they are going to be um, studied by machine vision, and then machine vision collect all these images, collect all this information, and is going to send to the algorithms in computer vision to analyze them, and then computer vision is going to say, or is going to allow the self-driving car to distinguish or identify the different things that we have in the scene or in the environment. That is just one of the applications. We have a lot of applications also in medicine, agriculture, the processing, industrial processings, taking care of different machines, taking care of different parts of the environment. So there are a lot of applications in which artificial intelligence with computer vision, machine vision, and image processing are helping us to solve a lot of problems that the society has in the real life. Next, okay, but how it is working? Well, what we want with machine vision and computer vision is to mimic what the human brain is doing when it is seeing something. When a human brain is seeing something, it recognizes what is the object, and it also have the context for the environment of what is he or she seeing. So by example, in this case, we can see the image of a cat. We know that this is a cat, and then automatically we say, okay, this is a cat, and we know about all the other things that we can have around it. We know that it is soft, or that it can be angry and maybe dangerous, but that it can be sweet. And by the other hand, the machine, the computer is going to detect a cat. But this detection is going to be because it is the machine is going to be able to detect the cat because it has been exposed to a lot of images of cats. But to that images, we need to make an ontology or a dictionary of all the terms that can be related with the cat. That is the softness, that is that maybe it can hurt, that it needs to be fed. All of these things that we know as humans, because we are very good learning those things from the environment. That things we need to explain to the machine that this object, the cat, is going to have or is going to be linked with all of that actions or sensations. So at the end, what we want to do is that the machine recognize this cat and knows that this cat is not so dangerous. It can be dangerous, but not so dangerous. That can be very sweet. That we need to feed. That we need to take care of him or her. And that is all of that knowledge is what we want to give to the machine, to be at least a little bit more like a human. It's impossible in this moment, or it's impossible to think like a human because the human brain is very, very complex and is very extraordinary. But we want that these machines knows more about the environment just because they can help us in one moment that we need them. So before we go with more complicated things and examples from the real life, I want to show you some things that are fun that we can do with computer vision. I'm going to present you with, I'm going to run this algorithm, and I would like to show you something that we can do with it. I'm going to go for something that I need to show you what we can do. So ideally, in this moment, you are going to be able to see me, and then I'm going to show you mimic of the of Harry Potter tool for invisibility. So in this moment, what I am doing is to use computer vision to get myself invisible for you. That this is one thing that it's amazing, that is interesting, that is fun, and that can help us to just maybe do another things that are more with more applications. But in computer vision and science, we want to have fun sometimes. So this is some of the thing. This is one of the things that we can do with computer vision. So we have the invisibility clock from Harry Potter. Well, maybe you would like to know how I can do this or how we can do this. So I'm going to explain a bit what is happening behind the scenes. First, let me check. It's okay. I hope that you are seeing my my screen with the code. what we do in this moment, or how this is working, is just the code is opening the camera, is taking in one moment all the scenario that is behind me, and then is segmenting the background with the foreground. In that way, all the background is stored frame by frame in one part of indeed in this variable that we call background. Once it is stored, then in the next frame, when I sit again with the tissue, that in my case I choose the red color, then we say to in the algorithm that we are going to highlight the color, the red color, and that we are going to blur the background, and then we are going to make a mask that is like just segmenting one part of the image. In this case, we are telling in the algorithm that we want that segment only the part in which it detects the red pixels. And then it is going to change the image when it is in the next frame in the video. When I sit and I put on my clock, it is going to change the pixels that detect with red color. It is going to change for the pixels that are in the background. So that's it. That's the part that is doing all the magic behind the scenes, and it is just something that can be very, very fun. And we, as we do this thing, masking or segmenting the background, we can do with this a lot of things, a lot of more things. By example, in the real life, we can just segment all the, maybe not all, but some things in the scene, and then with the algorithm, we can know which is in front, which is behind of the things, and we can choose what we want to keep, what we don't want to keep, and that can help us to just select, by example, in a medicine, different cells from others to differentiate them. That can help us also to classify different things in the environment. That can also help us to detect some damage in some things. And that is what we are doing and we are going to see in the next slide. In this case, I was working trying to detect the road, the distress, and the scene in the road, in the streets. To do this, I used an algorithm called UNet that is using different convolutional neural networks to max boolean and then concatenated it to reproduce the same image, but detecting the things in that we found in the scene. So this is the learning curve. It says how the machine is learning, and if we found that we are happy with the results, then we just keep the model. Here is an example. We have the one picture, one image from the street, and then we can segment it. This labeling is called annotations, and then from this, once we feed the algorithm with with a bunch of images, the algorithm is going to learn. It's going to learn that this part, these pixels with this color are the pixels that belongs to the road. And then it is going to give us the segmentation of that road. And then as we can see here, we see a lot of read. Then we just, in this case, we just need to make a binary decision just to segment the part that we want to segment. So this is one application. These are the same examples, and the time of computer, it depends of the machine that we that we are using, but for a quantity of 2,000 images, in between 100 and 2,000 images, the time is like around 410 seconds. So it's not bad. Well, we need to do a lot of training in the algorithm to get the best model, and also we need to check we need to review all the learning curves just to know which is the best model and how we can improve it. Because when we are training one model in deep learning using neural networks, we have what we call hyperparameters, that are a lot of parameters. Well, not a lot, but they are a set of parameters that we need to tweak just to have the best model. But it can, sometimes if we saturate the neural network, then we start to decrease the accuracy, and we need to keep a control in between how we manage the hyperparameters. So these are more predictions and some correlations that that are sometimes are helpful just to understand what we need to move or to balance in the neural network. Also, as I said, my example here, also we can choose between different images, and we can choose in the part of the machine learning, in the part of the machine learning and in the part of machine vision, which is the best algorithm and which is going to be the best device to get the best results. So in this case, by example, we were testing with another device to get the best images, or the best information from the images, because at the end, in this project, what we want to do is to get the distresses in the road, and that is complicated because we have sometimes these distresses are similar to the shadows, and that similarity makes that the algorithm and the model confuse one with the others. So we try to do or we try to change the devices that are taking the images, and in this moment, maybe something that can help us, or that can help in this kind of projects, is to use lidar images, because that can give us the depth. So that could be an interesting thing to test in this kind of projects. Okay, the development of the model. The workflow is like in the workflow in production or in industry, it's a little bit complicated because we should have we should be very, very careful with how we collect the data, as I said, the devices that we use to collect data, how we are going to store the data. In these cases that are images, the images, they need a lot of space to be stored. And then we need to label the data. That is the process of the data annotators. For that, we need to have the annotators, they should have experience with the images and with the project and the problem that we want to solve, because it depends on the annotations how the model is going to learn, how the neural network is going to be trained is the most important part and all the characteristics that we need, we are going to get them from the annotations. So that is a very, very important part, and it takes almost more or less the 70% of the time. So in the project, so in between the annotations and the pre-processing, if we use data augmentation, then it can be a little bit faster, but we need to be careful because with data augmentation, maybe we can saturate. We are going to saturate the model, and it is going to start decreasing the accuracy. So we need to find a balance in between the data augmentation and the annotation, the real annotations that we are using. Once we have the pre-processing, the annotations, the pre-processing, the data augmentation, then we start the training. With the training, we get the model, and we know, in that moment, we evaluate if the model is good or not. If we are happy with the model, then the model is going to go to production and start doing predictions. But if we are not happy with the model, then we need to return to, okay, review again the annotations. If they are okay, then we need to modify the hyperparameters, maybe something wrong there, or maybe we are doing a lot of data augmentation and it is not helping us with the training. Then it is like a recursive process, and still, if we are happy with the model, we can have an accuracy maybe 7.7 accuracy, but and we can be happy with that, and we can send to production, but we want to have a better accuracy. So to do that, we need to review all the process, manipulate some things, and keep tracking of all the things that we are changing. That is a lot of work in the R&D section. Then one of the things, the important things is the data selection. Which is the data that we need or that is best for our proposal or for our project, for our problem. Then we need to discuss about the image size, the quantity of pixels, and also in these cases, by example, the date, because the timing, the year, if it is raining, if it is cloud, if it is very sunny, if we have shadows, all of that are important factors that can complicate or help with the training of the algorithm. And the data annotation is the other part that is very, very important. In the data annotation, we need to have, as I said, people that is an expert in what they are doing. They need to detect, by example, in this image, the cracks and differentiate them from the other things. They need also to know which kind of cracks they are, and that is not easy to segment this this image, by example, it can take like a half of hour to do this, from half of hour to 1 hour, and that is very costly. But at the end, this data is very important data, and it can be sold also. But the thing here is that we should have we should have a lot of care with the details, because the details are going to be the important part in any study of image of computer vision, image recognition, and machine vision. Then yes, we can have some images that they are easy to segment than others. We should decide if we want to segment everything in the scene, and if we are going to segment everything in the scene, if we are going to use that for another things. And also, for example, when we have pixels that have the same color than others, and they are different things. Like in this case, if we want to segment the trees and the grass, they can have the similar color of pixel. Then we need to use the context. The context is going to give us, or going to give the algorithm the clue to classify the grass, to separate the grass from the trees. That gives us that we should have like a taxonomy about the concepts that we need to in what we want to segment. Then we should, if we have a project in this like this, we need to know about all the terms and all the objects that are related with that scenario, and make a taxonomy. So in this case, this is the taxonomy. We need to also know about what happened or what produced the phenomenon that we want to study, and because that is going to help the algorithm to learn better. Well, that is the part of the labeling. There are a lot of complications when we are labeling. We need to be very careful with the pixels. We need to be very careful with what we are segmenting, and have a hierarchy of segmentation. And as I said, this is the part that is very, very important, and is also at the same time complicated, but is how we can teach the machines to learn what we are seeing. So this is the different set of images and the work that we need to do when we are segmenting, and when we want to give context to the machine. By example, here we have a fountain, and we know that maybe we can have a valve near the fountain. That is going to be the context that the algorithm is going to need, because maybe the valve in the ground can be interpreted with like a crack, but it's not a crack. So these examples are going to make the algorithm with a better accuracy, and it's going to give better predictions. So in annotations is everything that I have, and I think that we can start with the questions.
Okay. So does anyone have any questions? You can either type it on the chat or just unmute yourself and ask some questions. Okay. Um, well, I have a question. So, in my case, when I mustered data for or images that are used to train a model on images, I often saw that the label was only like a name. For example, cats and dogs. Like I would have images of cats, and then the label would just be the name. Um, why would be coloring the image be a better labeling, or in this case?
In this case, because we are segmenting and we are, like in the example of the cap, we are going to detect each pixel that belongs to each one of the colors that we have or that we are using in the mask when we are making the labeling. So if we are choosing the color blue to label the grass, by example, then the algorithm is going to know that that grass, that pixel that is in blue is related with the grass and is related in the same way with the pixel in the image because of the position.
Okay. Anyone else has a question? No, I don't see any hands raised. Okay, so I don't think anyone else has questions. So thank you very much, Margarita. It was really, really interesting. Yeah, and hopefully I'll see you in the gather.town in the networking event. Um, but yes, so thank you everyone for coming. Next up, it's the networking event, the networking fair. So be sure to join us on gather.town. So thank you again.
Thank you. I hope that you enjoy
Yeah, it was really good. Thank you.
it. Bye bye.
Bye.